Hello friends, warm welcome to all to the channel World of Zoology. Next point from our previous chapter, that is instrumentation, which is colorimetry. We'll discuss same in this lecture with respect to 2 points: introduction and then application, principle and application. First we'll consider the introduction point of the colorimetry instrument. When electromagnetic radiation interact with a matter, it may be reflected back, that means completely return, absorb completely, that is penetrate the matter, partially absorb and allowing some to pass through, that means some of the electromagnetic radiations are absorbed within the matter and some are allowed to pass through the matter. When light is reflected back, the matter interacting with such light is polished surface. For example, mirror or a metal. On that particular shiny surface, light is reflected. Completely absorbed light indicates that the matter is an opaque body. It may be black body, and therefore the light is absorbed by that particular matter. Partial absorption of light gives color to interacting matter when the light is not absorbed in the visible region. That means partial absorption of light is responsible for giving color to that particular interacting matter, as the light is not fully absorbed in the visible region. The branch of science that studies the interaction of matter with electromagnetic radiation is called spectroscopy. In our today's lecture, we'll consider principle and applications of the colorimetry. First of all, principle of the colorimetry. The amount of an analyte in the given sample which is placed in the cell of a known path length. It may be estimated by allowing it to interact with electromagnetic radiation of a certain fixed wavelength. The fixed wavelength, which is of the maximum absorption, or lambda max, in the visible region, and measuring the intensity of the transmitted electromagnetic radiation by such sample. The electromagnetic radiation used for this purpose is generally in the visible region of the electromagnetic spectrum. Light visible to human eye, it ranges from the wavelength 300 to 700 nm, which is used or use is made for the fact that light of certain wavelength may be absorbed by analyte in preference to all other wavelength. Means the light of a particular wavelength may be absorbed by analyte, which is to be considered or studied in preference to the other wavelengths. The wavelength of light absorbed by the analyte depends upon the principle of the complementary colors. That is, if all the wavelengths of light are absorbed by a transparent solution except yellow, then yellow color is allowed to pass through. So such matter appears as yellow, whereas blue color light is predominantly absorbed. Conversely, if the matter predominantly absorbs yellow color, that means when the blue color is absorbed, the matter appears yellow, and when yellow color is absorbed, the matter appears blue. Conversely, if the matter predominantly absorbs yellow light, it would appear blue, since it is this blue light that would be allowed to pass through a particular matter. The chart which shows the absorbed wavelength and observed color in the table. Wavelength in nm is the first column. At 400 nm wavelength, light absorbed by the matter is violet, and therefore the color shown by the matter will be yellow-green. At 435 nm, blue color will be absorbed by the matter, and consequently the color shown by the matter will be yellow. At 495, green color absorbed by the matter, and the color shown will be purple. At 560 nm, yellow color is absorbed by the matter, and then the complementary color will be blue. At 650 nm, color absorbed by the matter will be orange, and naturally the color shown by the matter will be greenish blue. At 800 nm, red color will be absorbed by the matter. At the same time, color shown by the matter will be bluish green. The principle of complementary colors is used while selecting a particular filter in colorimetric estimation. The color of filter is complementary with reference to the color of the analyte, which is to be considered. Colorimetric technique works on the basis of Beer-Lambert law. This is also called as Beer's law. Lambert studied the relation between the path length and intensity of the incident and transmitted radiation by an object of thickness b. He found that the log I0 divided by log IT is equal to k times the thickness b of the object. That is, log I0 by IT will be equal to kb. That means k times the thickness b of the object. Beer studied the relation between the concentration and intensity of the incident and transmitted radiation. Remember that in the previous law, that is Lambert law, the relation between the path length and intensity of the incident and transmitted radiation is considered. Whereas here in the Beer's law, the relation between, we can memorize the term BC for that, that is Beer's law with the concern with the concentration. In the Beer's law, the relation between the concentration and intensity of the incident and transmitted radiation by a sample of concentration C is studied. Interestingly, Beer found that the log I0, that is incident light intensity, divided by IT, that is transmitted light's intensity, is equal to K dash C. Combining the two equations, it is easy to see that I0 by IT is equal to K dash C B, or I0 by IT is equal to ABC. By combining the two constants, that is K and K dash, into one, which may be expressed either as A or A0. The ratio of log I0 by IT, that is initial or incident light divided by the intensity of the transmitted light, is called as absorbance, that is capital A, or optical density OD. We shall be using the terminology absorbance, that is capital A. Thus we can express absorbance capital A as A is equal to ABC, or that is capital A, naturally capital A is equal to A0BC, where A and A0 is absorptivity of the sample. That is, it is the absorbance if the path length is B in centimeters and concentration C, both are unity. B is the distance to be traversed, that is distance which is passed or traversed, that is path length, by the light wave in the in and C is the concentration of the analyte. That means B is the path length, that is distance through which wave is traversed or travels, and C is the concentration of the analyte. When the concentration is expressed in terms of moles per dm cube, the symbol A0 is used, which is called as molar absorbability. The concentration is expressed in any other way, means when the concentration is expressed other than moles per dm cube, that it may be in the terms of the percentage or parts per thousand, that is ppt, or it may be expressed in terms of parts per million, that is ppn, then small a is used. In other words, Beer's law states that absorbance, that is capital A, which is also known as OD or optical density of an analyte, is directly proportional to the concentration of the analyte. Since more the concentration, more is the absorbance of the light. That means for transparent solution, less light will be absorbed. Usually for analysis, a cell or cuvette is used to place the sample. Therefore, path length B is constant. Absorbability will then depends only upon the nature of the absorbing sample, and hence under such circumstances, absorbance is linearly related to the concentration of the analyte in the sample. That means absorbability directly proportional to the concentration of the analyte in the sample. It must be understood that the sample under investigation must be colored with respect to the analyte that is to be assayed or estimated. However, if the analyte itself is not colored, then the sample has to be treated with a suitable reagent, which would give a colored product, linearly related with the amount of the analyte present in that particular sample. For example, if one has to estimate the phosphate present in a biological sample, since the analyte here is colorless, it may be treated by suitable coloring reagent. Say that particular reagent is ammonium molybdate. That would give a canary yellow product, and the absorbance of this canary yellow product will be linearly related to the concentration of that particular analyte, which is known as here phosphate, present in the sample. Most instruments have a scale that shows reading in terms of absorbance, that is capital A, as well as transmittance percentage. It is important to appreciate the relation between the capital A, that is absorbance, and percentage transmission. When all the incident light is absorbed by a sample, the intensity of the transmitted light will be 0. That means intensity of the transmitted light will be 0 when all incident light is absorbed by the sample. Similarly, when no light is absorbed by the sample, all of the light will be assumed to be passed through the sample, and hence the intensity of the transmitted light will be naturally 100. Means 0 absorbance, 100% transmission. 100% transmission is zero absorbance. On the contrary, 100% absorbance means zero transmission. A is related to T by a relation A is equal to log to the base 10 I by T. It should be remembered that Beer-Lambert's law is applicable only for dilute solutions having concentration less than 10 raised to minus 2 moles. The reason for this is that for more concentrated solution, refraction of the light interferes with the absorption of the light. Here, the digital colorimetry instrument is shown and the old one is also shown. In digital instrument, the direct OD is given, the value of the OD or transmission is given. Whereas in the old one, the transmission and absorbance, both values can be given because of the relation which is explained by me previous in the same lecture. The knobs are there, sample holder, that is for placing the cuvette or the cell into that. Then the power switch on, switch off is shown. Transmission and absorption scale is there. Light control, wavelength control, these are all buttons for controlling the colorimeter manually. Whereas in case of digital colorimeter, the sample is placed and we can read out the percentage transmission or absorbance. Now we'll consider applications of the colorimetry. First application is to determine the amount of analyte present in the sample. This is usually done by first obtaining calibration curve by measuring the absorbance of the series of standard solutions of known analyte concentration from the colorimeter. A graph of A absorbance on y-axis against concentration on x-axis is then plotted. This graph is called calibration graph and ideally which is a straight line graph passing through the origin since no analyte, that is blank, means no OD. Measurement of the OD of the solution containing unknown amount of the analyte will then give the concentration of that particular analyte in the sample under investigation using this standard calibration graph. Second application, if the molecular weight of analyte is known, molar absorptivity of such analyte may be obtained. Third application, colorimetry may also be used for performing titration to determine the strength of the given solution in terms of grams per liter. Such titrations are called photometric titration and are possible if any one of the three essential components, that is titrants, solution of the known concentration, titrant, that is solution of the unknown concentration, and third one, the product of the titration absorb light of a given wavelength. Fourth one, colorimetric analysis can be used for following a progress of a given chemical reaction with time, which is known as chemical kinetic. That is, we can calculate the progress of the given chemical reaction as the time passes. For example, activity of certain enzymes such as amylase, which is amylolytic enzyme for digestion of the starch, that is a complex carbohydrate, may be measured by using colorimetry. As the time passes, the amount of the analyze which is converted into simple sugar will become less and less and will be converted into simple sugar, and the reaction of the mostly starch with that of the iodine is considered for giving coloration to the particular sample. As the digestion proceeds with the time, the color will become faint or the pale, in that case pale blue, as the substrate, that is starch, is converted into product, that is simple sugars. Thank you for watching this video. If you like the video, like it. If you share the video for the benefit of the maximum students, and subscribe the channel World of Zoology for the notification of my next video on the spectroscopy.